So we've already seen that this statement is going to be false, and you can watch my previous video to see why. But what if instead of having the intersection on the right-hand side, we instead had the union? Is this now going to be true? Well, let's draw some examples. Okay, so in the first example here, we have all three sets have something in common with each other. We have our set A, B, and C. Let's draw the left-hand side. The left-hand side tells us we're going to be looking at the intersection between B and C, which is going to be this region shaded in blue. And then we're going to want to take our set A and shade in all the parts that do not share something with the blue section. So that means we're going to shade in the following region. Right, the reason we shaded this region and not this middle part is because this middle part here obviously is shaded in by the blue part, and we don't want to include anything that's in this blue part. So there we go. Are we going to find the same shaded region on the right-hand side? Well, let's have a look then, right? If we take our sets A minus B, what is that going to be? Well, that's going to be everything in A that's not in B. So we're going to want to shade all of A that is not going to be in B. Fantastic, okay? What about A minus C? Well, A minus C is similarly going to be everything in A that's not in C. So that's going to include this region right here. And what do we find? We want to take the union of the blue and the red. So what shape, what region are we looking at when we're looking at both the areas that have blue and the areas that have red, or at least one of the two colors? Well, you'll notice the area is going to be identical to the orange section here. Like so, right? These are identical on the left and right-hand side. So that means that for this relation between the three sets, this statement is going to be true. Okay, what if in our second case, the three sets have absolutely nothing in common with each other at all? They don't share anything. Well, then B intersect with C is going to be nothing. There's no intersection for us to shade in. So A minus that nothing is just going to give us back our original set A. So we just shade in all of A. Okay, now on the right-hand side, we should expect to also only have to shade in all of A. So what is A minus B? A minus B is going to be everything in A that's not in B. Well, since all of A is not in B, we can just shade in all of A. Similarly with A minus C, what parts of A are not in C? Well, it's going to be all of A. All of A is not going to be in C. And what do we find? In both cases, we shaded in the entirety of A and nothing more or less. So in this case, this is also going to be true. Now let's just check a few more examples. Okay, so in these two examples, we have two sets share something in common, but the third set doesn't share anything in common with the other two. So what if A shares something with B? Well, B intersect with C is still going to be nothing. We don't have to shade anything in because they don't intersect anywhere. So what are we going to do? We're going to say A minus that nothing is just going to give us back our original set A. So we're just going to shade in all of A, like so. Are we going to get the same on the right-hand side? Well, A minus B is going to be all of A, or maybe let's do this in a different color as I've been doing. It's going to be all of A that's not in B. So that means we're going to shade in all of this, but we're not going to shade this middle region because this middle region is also in B. Okay, what about A minus C? Well, A minus C is going to be all of A that's not in C, and since none of A is in C, we can just shade in red all of our A. And now we want to take the union, so we want to look at every region we've shaded in. This means that we want to look at the regions that are red, the regions that are blue, and the regions that are both. And of course, when you're looking at that, overall, you've just shaded all of A, similar as we did on the left-hand side. So that means that this is going to be true for this case as well. What about this bottom case? What if our A doesn't share anything in common with these? Well, what do we find? A intersect with B is going to be this region right here. And then we're going to say, let's take everything in A that's not going to be in this shaded region. Well, everything in A that's not in this region is just going to be all of A, since A doesn't share anything with that shaded in region. Okay, what about here? Well, here, we're going to find something similar. We're going to say, okay, A minus B is going to be everything in A that's not in B, and since all of A is not in B, we can just shade in all of A. Similarly, for A minus C, we can shade in all of A because none of A is in C. And we find that in both cases, we've shaded in the entire set A. So it looks like the left and the right-hand side also match in this case. Obviously, we're not interested in this blue part. So there we go. The left and the right-hand side do match. We just have 2 more examples to go before we can officially be confident that this is going to be true. I've actually opted not to do those 2 examples because it would be a set within a set within a set, and then there's different combinations of that you can obviously do, so that's way too many combinations. I'm just going to say 4 examples. I think that's enough for me to go off of and assume that this is going to be true. So how are we going to prove that this is true? Well, for 2 things to be equal to each other, it must mean that everything on the left-hand side is on the right-hand side, and vice versa. Everything on the right-hand side is on the left-hand side. So that means we have to prove that the left-hand side is a subset of the right-hand side, or as I said, everything here is going to be here, and vice versa. The right-hand side is a subset of the left-hand side. Everything here is there. And once we've shown that this is true and that is true in our proof, we can then conclude that that must be true. So let's go ahead and start that. So to start our proof, recognize this is going to be a for all proof because we're looking at all sets A, B, and C. So this means we start with a let. We say let A, B, and C be sets. Okay, and now we can get into our first case. So in order to prove the left-hand side is a subset of the right-hand side, we have to show that any element, for example, x, that's going to be in the left-hand side, is also going to be on the right-hand side. And once we've shown that any element on the left can be on the right, we can then conclude that the left must be a subset of the right. So we want to start here, and our goal is to get to this set here. So what do? Well, what does it mean for a set, for an element, for something to be an element of this set? Well, it means that x must be an element of A, and x must not be an element of B intersect with C. Okay, so what does this mean then? For x to not be an element of B intersect with C, it must be that x is either an element of B we have 2 cases, right? For this to be true, it means x has to be in both B and C. However, for it to not be true, it must be that x is either only in B or x is only in C. So it means that we get 2 cases. The first case looks like x is going to be an element of B and x is not going to be an element of C, or it's going to be that x is going to be an element of C and not an element of B. Is that even appearing on the camera? It is, but I may be blocking it, but that's okay. We know that it's going to be one of these 2 cases, so we're going to have to show both of these cases lead to our conclusion. Okay, well, what do we know? We know that, Okay, so how can we get from this case to our finale? Well, we know both cases mean x has to be in A. So, okay, if we take this case, x has to be in A and x has to be in B, which means x cannot be in A minus B. So this means x cannot be an element of A minus B. However, because x is not in A, we know that x will be an element of A minus C. So we get from here to here, and if it's an element of A minus C, then it'll obviously be an element of A minus C unioned with anything. Okay, I think it's going to be the same on the right-hand side. If we say x is an element of C, then we know x is not going to be an element of A minus C, but x will be an element of A minus B by these on the right, which is going to lead us to the same conclusion as we did here. Okay, so we have the sketch of our proof. Now let's actually put that into words. So first we start by creating this representative element x. We say, suppose x is an element of A minus open bracket B intersect with C. Fantastic. We then say, then x is an element of A and x is not an element of B intersect C. We then say, for x to not be an element of B intersect C, it must be that x is an element of B and x is not an element of C, or x is an element of C and x is not an element of B. Fantastic. Now we break it down into our 2 cases that we've created. We say, if x is an element of B and x is an element of C, or is not an element of C, then x is an element of A minus C since it's still, or I'm not even going to bother saying since it's still an element of A. We can then say that since it's an element of A minus C, we could say so x is going to be an element of A minus B unioned with A minus C. Fantastic. And now we can say similarly, if x is an element of C and not an element of B, then x is going to be an element of A minus B, making x an element of A minus B unioned with A minus C. Fantastic. And now we can conclude that thus A minus B intersect with C is a subset of A minus B unioned with A minus C. Okay, so we've shown the first case to be true. Now let's try the second case. Okay, so similar to how we did in the first case, if we can show any element in our first set can also be an element in our second set, then because any element in the first is in the first set is going to be a subset of the second. So in this case, I'm going to use y to distinct ourselves from the first case. So what does it mean for y to be an element of the first set? Well, it means that y is an element of A and y is not an element of B, or to be unioned with, y is an element of A and y is not an element of C. Fantastic. Okay. Or actually, I think I should do a more explicit job here. This means that obviously y is an element of A minus B, or y is an element of A minus C. And then what does it mean for y to be an element of A minus B? This means y is an element of A and it's not an element of B. Or we can say that for the other case, for y to be an element of A minus C, it must be that y is an element of A and it's not an element of C. Fantastic. Okay. Well, if y is an element of A and it's not an element of B, we know that because it's not an element of B, it can't be an element of B intersect C, because for it to be an element of B intersect C, it must be that y has to be in both B and C, but it's not in B, so it can't be in here. So we know that since y is in A and it's not in here, then we know from these two, we get to our conclusion. Y is obviously in A, but it's not in B intersect C. Similarly, on the right-hand side, since y is not in C, y is not going to be in B intersect C, which means that since y is in A and it's not in here, then it similarly leads to our conclusion there. So now that we have sketched our proof, let's actually put this into words. We're going to start by supposing our representative element y. We're going to say, suppose y is an element of A minus B unioned with A minus C. Fantastic. We can then say, then y is an element of A minus B, or y is an element of A minus C. Okay, now let's break it down into the case where if it's an element of A minus B. If y is an element of A minus B, then y is an element of A and y is not an element of B. So if y is not an element of B, then y is not an element of B intersect C. So, or I'll just say making y an element of A minus B intersect C. Fantastic. Okay, and similarly, if y is an element of A minus C, then y is an element of A and not an element of C. So if y is not an element of C, then y is not an element of B intersect C, making y an element of A minus B intersect C. Fantastic. And now we just have to conclude what our second case was trying to show. So we can say, therefore, A minus B unioned with A minus C is a subset of A minus all open bracket B intersect with C close bracket. So there we go. We've shown the first case to be true and the second case to be true. So now all that's left is going to be just write our conclusion. We say that in conclusion, since this is true and that's true, that must be true. So there we go. We've proven that this statement is in fact going to be true.